Chapter 4, Part 3, which is about the effect of chemical reaction equilibrium plus chemical kinetics on reactor performances. Two major factors that limit reactor performances include: the first one is chemical reaction equilibrium. The second one is chemical reaction kinetics. Shortly, equilibrium, then kinetics. So let me start with the equilibrium. So chapter 4a is chemical reaction equilibrium constant K of activity. As you know, at chemical equilibrium, the concentration of reactants and products do not change with time invariant, like the steady state. How to quantify the equilibrium? Of course, that is the K. As you know, that is the chemical equilibrium constant K, based on activities of species included in the chemical reaction. Ka, again, the chemical equilibrium constant K of activities is equal to the product for all species I of the activity of I species at equilibrium to the stoichiometric coefficient. I'd like to emphasize the equilibrium. In this case, to calculate the chemical equilibrium constant Ka, you should use the activity at equilibrium. I'd like to emphasize again equilibrium. Here is the example. 2A plus B is going to the product plus some waste. So the equilibrium constant of activity is the activity of A at equilibrium to the minus 2. This comes from the stoichiometric coefficient of the species A. And how about B? Activity of B at equilibrium and minus 1. Then how about P? Plus 1. How about W? Plus 3. So finally we could obtain this description of the equilibrium constant K of activities for this chemical reaction equation. What is the meaning of activity? Activity is effective concentration or mole fraction of a compound in a multi-component mixture. If you have the species I in the vapor phase or gas phase, the activity of the species I is approximated by the partial pressure, which is the product of the mole fraction of the corresponding species I with the total pressure per 1 atm. How about liquid phase? Mole fraction of the species I represents the activity of the corresponding species. The next one is solid. Independent of the identity of the species I, if you have a solid, its activity is equal to 1. Please memorize those three basic the representation about the activities. Also, during this course, I'd like to assume several things. If you have vapor phase compounds, then you could assume that vapor behaves as an ideal gas mixture. Of course, sometimes not. However, in this course, for simplicity, we will use the ideal gas mixture for vapor phase compounds. How about the liquid phase compounds? The first liquid phase compounds would be solutions. Solution means we have some solutes inside of the solvent. So in that case, if you have a solution, the solution should be dilute solution. Okay, it means there are no very strong interaction between solute molecules inside of the solvent. The second type liquid phase compound is the multi-component liquid mixtures. In this case, we will assume that the liquid molecules for making the mixtures are of similar size and chemical types. It means we will not consider any specific interaction between the liquid molecules. For solid phase compounds, we will assume that solid phase is pure. Let me think about the dimension of the equilibrium constant of activities. Activity coefficient A sub I for species I is basically dimensionless. So the equilibrium constant of activity should be dimensionless. However, practically, sometimes the equilibrium constant would have a unit, especially for vapor phase reactions. I have said the activity of species I in the vapor phase is approximated by the partial pressure per 1 atm. But practically, we forgot the use of this 1 atm. Practically, we will ignore the 1 atm. It means the unit of the activity of species I has some pressure unit. So, the equilibrium constant of activity is product of the partial pressure to the stoichiometric coefficient. P is the total pressure, and then we can get the total pressure P out of the product operator, because P is constant for all species I. Then P have the summation of the stoichiometric coefficient. So P to the summation of the stoichiometric coefficient I as a sum. So if we don't have this value is 0, then the chemical equilibrium constant should have the unit, maybe pressure unit. This is the common practice, but not rigorously correct. So for example, ethane is combusted by the help of oxygen, then we will have CO2 and H2O after the complete combustion. So during this reaction, the total moles of compounds involved in this chemical reaction equation would increase. Let me check it. For the product we have 5 moles, but for the reactant we have totally 1 plus 3.5, so 4.5 consumed. So net the net of the stoichiometric coefficient is equal to 0.5. It means the moles of reactant is larger than the moles of reactant. Okay, moles of product is larger than the moles of reactant. So in this case, the equilibrium constant should have the unit like atm to the root square or something like that. Example 4.14. Let me think about the equilibrium constant. Derive equations for equilibrium constant of activities in terms of mole fraction and pressure for the following case. The first one is the gas phase synthesis. So ammonia gas, hydrogen in gas, nitrogen in gas, hydrogen in gas, and ammonia in gas. So Ka is equal to ammonia to the 2, and nitrogen to the 1, and hydrogen to the 3. Okay, then activity can be approximated by the partial pressure because those three compounds, including nitrogen, hydrogen, ammonia, are in a vapor phase. So Yp, Yp, Yp. And then let me get together the mole fraction. So we have this term with the total pressure have the -2 here. So because the total summation of the stoichiometric coefficient is 2 minus 3 minus 1, so -2. So on the right hand side of this equation you have the 1 over p square. The second one is the synthesis of aspirin in a dilute aqueous solution from salicylic acid and acetic acid. So those compounds are included in water-based reactions. So liquid phase. And this is for this is for A aspirin, and this is for the water, and the other thing is SA, maybe this one, the other thing is acetic acid here. So everything is liquid, but you should recognize that the solvent molecules, the activity of solvent molecules is assumed to be 1. So in this case water is the solvent molecules, so it is going to 1. So this is the result. How about solid? The reduction of barium sulfate or to barium sulfide. Barium sulfate solid, barium sulfide solid, and carbon monoxide and carbon dioxide is the gas. So barium sulfide here and CO2 2D4 here, and barium sulfate 2D1 here, carbon monoxide 2D4 here, and barium sulfide and barium, no, something wrong. This is the barium sulfide, this is the barium sulfate. So both the activity of both solid molecules should be assumed to be 1. So 1 and 1. Also the other thing is gas, so I have represent the activities of gas phase by the mole fraction with the total pressure, or actually partial pressure. So we have this one, and the net of stoichiometric coefficient of this chemical reaction equation is 0, like 5 from 5, so 0. So we don't have any term of total pressure in the description of the Ka. You have learned about the definition of equilibrium constant of activities. Then how to calculate the equilibrium constant from thermodynamic information. Let me start with the Gibbs free energy. G is Gibbs free energy here, and which is the energy state of a system. The value of G is at a minimum, not 0, when a system is at equilibrium. Then let me think about the Gibbs free energy change of reaction. That is the change in Gibbs free energy as the reaction proceeds from reactant to product. Therefore, this is the thermodynamic driving force for converting the reactant to the product. It's time to define the standard state. The standard state indicates the 25 Celsius degree and 1 atmospheric pressure. Actually, the exact meaning of the standard state is the condition at which all of the species have the activity equal to 1 at 25 Celsius degree. So in this case, 1 atmospheric pressure indicates the activity is equal to 1 at 25 Celsius degree. Anyway, the Gibbs free energy change of reaction with this circle indicates the standard Gibbs free energy of the reaction at the standard state, this condition. And okay, so right now we have the Gibbs free energy change of reaction and also its standard state version of the Gibbs free energy change of reaction. So let me think about the thermodynamic equations. The Gibbs free energy of reaction at any temperature T is equal to Gibbs free energy at the standard state. Of course, still this is related to the reaction, plus ideal gas constant with temperature and log of the quotient, which is the reactant to product. I mean the activity of reactant to product. No. Activities of product to the activities of reactants. That is the so-called quotient. At equilibrium, the delta Gibbs free energy is going to 0. So, and also at the same time, Q is going to the equilibrium constant. Then, from these equations, you could obtain the value of equilibrium constant if you know the value about the standard state Gibbs free energy change of the reaction. So again, we could use this equation. Equilibrium constant of activity is equal to exponential of the minus Gibbs free energy, actually the standard state Gibbs free energy of reaction per RT. This equation is practically used at 25 Celsius degree. Approximately, however, not at 25 Celsius degree, this equation is used. Again, log of the equilibrium constant of activities at certain temperature is equal to minus 1 over ideal gas constant with something. And here we have two terms. The second term is related to the temperature dependent term, and here is the enthalpy, standard state enthalpy of reaction per temperature. The other thing is the constant term, and delta G Gibbs free energy at the standard state of reaction minus delta enthalpy of reaction at the standard state per 298. Actually, this is going to the 25 Celsius degree. So at 25 Celsius degree for temperature T, then this equation is going to this one. So actually almost the same thing, and the more generalized version is here. So please use these equations for solving your problems. Then one more thing. Okay, so how can we obtain the standard state value of the Gibbs free energy of reaction and also enthalpy? Each one can be calculated from the standard free energy change of formation or standard enthalpy of formation. What is the formation energy? Here, standard free energy change of formation. Let me say just the formation energy. Formation energy is the Gibbs free energy change to make a compound I from each element in their natural gas and state of aggregation. For example, let me say about the formation energy of the CO2. So CO2 is here, and these compounds can be made from carbon. This is the element plus O2, and the Gibbs free energy change of this reaction is called standard the free energy change of formation for the CO2. Okay, so in appendix B you could find a lot of values about the standard free energy change of formation or standard enthalpy of formation at the standard state can be found in Appendix B. This formation energy is 0 for elements at 298 K, I mean room temperature, 1 atmospheric pressure, and in their natural phase and state of aggregation. So at 25 Celsius degree at 1 atm, the formation energy of carbon is going to 0 because this is the their natural phase and aggregation for element. This is the element. How about O2? O2 is the oxygen form in the natural phase. So the formation energy of carbon is going to 0. The formation energy of oxygen is going to 0. Then one more comment here. The equilibrium constant of activity strongly depends on temperature. Look at that. X-axis is the temperature, y-axis is the L and K. So sometimes the Ka is going up, sometimes Ka is going down. Then if delta H, I means the enthalpy of reaction, is less than 0, or I can say if your reaction is exothermic, the equilibrium constant decreases with increasing temperature. So it means this is minus sign. I mean the enthalpy value is less than 0. Then we have plus for the temperature term. Then temperature is going up, so the K value is going down. So this one. And how about if delta H of reaction, I means the enthalpy reaction of reaction is larger than 0 or positive value, then or if you have the endothermic reaction, then the equilibrium constant would increase with increasing temperature. Actually, of course, you can expect it from this reaction, but by using Le Chatelier principle, you can expect those trends. What is the Le Chatelier principle? Reaction goes to the direction to remove or change. So let me think about the exothermic reaction. So reactant is going to the product. Let me write down something. Some reactant is going to the product, and then this is the exothermic, so you have some energy there, right? And as you increase the temperature, so the reaction goes backward to the direction to remove the heat, because you are heating the system. So backward reaction is favored for the exothermic reaction when you increase the temperature, so Ka decreases. Let me think about the endothermic. R is going to product, and this is the endothermic. So the temperature is going down, right? And if you want to increase the temperature to the system, so the reaction goes forward to compensate the heat absorption by the reaction. So Ka increases with increasing temperature. So by using the Le Chatelier principle, you can expect the direction of reactions. Then also you can expect the change of the equilibrium constant. Again, please, you should be accustomed to the temperature dependency of equilibrium constant. Again, for the exothermic reactions, equilibrium constant is going down at high temperature. However, for the endothermic reactions, equilibrium constant is going up at higher temperature. Please memorize them. Okay, here is the table. The example 4.15. Ethyl acetate synthesis. Ethyl acetate. Okay, let me change the pen to the laser pointer. Ethyl acetate is an industrially important solvent, blah blah blah, and this is the ethyl acetate, which is made from those two things, ethanol and acetic acid. Then we have some values of the formation energy for the Gibbs free energy and also enthalpy. It means we could calculate the Gibbs free energy of reaction at the standard state and also Gibbs free the enthalpy of reaction at the standard state from the formation energies. Those four species are involved in those reactions. Then let me calculate the Gibbs free energy of reaction at the standard state. Is summation of the product of the stoichiometric coefficient of each species with the Gibbs free energy formation. So those things is going to here, the second one here, third one here, first one here. Then the summation of those four terms is going to plus 11.6 kilojoule per mole. Also, the enthalpy of reaction at the standard state can be calculated from the enthalpy of formation at the standard state. In the same way, and after summation, then we have this value. So plus sign is obtained for the enthalpy term. Therefore, it is the endothermic reactions. So at higher temperature, the equilibrium constant would go up. So by using this, by using Gibbs free energy term, then at 25 Celsius degree, equilibrium constant can be calculated by using this equation. Then it's about 0.01. At 80 Celsius degree, we could expect a higher value. It means 353 Kelvin. By using these equations, we obtain the 0.02 for the equilibrium constant at 353 Kelvin or 80 Celsius degree. So by using the formation energy, you could expect the equilibrium constant at any temperature. Here is another example. Example 4.16 about the synthesis of dimethyl carbonate. In this example, we will use the equilibrium constant based on activities for selecting pathway. The reaction to produce dimethyl carbonate, shortly DMC, here, from phosgene, here, is phosgene plus methyl alcohol is going to the desired product, which is the dimethyl carbonate plus hydrochloric acid. The problematic thing is here. What is that? That is the phosgene. Phosgene is very toxic compound. We are in the hunt for alternative reaction pathways for the production of DMC or dimethyl carbonate that don't require phosgene. We hate the phosgene because it is very toxic. Here are some under consideration. Then we have 4 different pathways: reaction 2, reaction 3, reaction 4, and reaction 5. In those 4 different reaction pathways, we don't need to use the phosgene here. Question is that which pathway would you pick on the basis of cost? So the first criterion is cost for selecting pathways. The second one is which on the basis of atom economy. Third one, which on the basis of chemical equilibrium, that is to say Ka, equilibrium constant of activities. Look at operating temperature of 100 Celsius degree to 500 Celsius degree as a reasonable range here. Here is the information to calculate the cost and also fractional atom economy. All compounds here, and for each compound we have the information about the molar mass and then also cost here. So let me try to calculate the cost and fractional atom economy. For example, here is the R1, reaction 1, including fusion. For synthesizing 1 kilogram dimethyl carbonate, we need to have 0.71 kilogram methyl alcohol and 1.1 kilogram fusion. This was calculated from the molar mass and the chemical reaction equations. By using the cost information, we could calculate the raw material cost. In this case, $1.91 for making 1 kilogram DMC. Also, we could calculate the fractional atom economy based on the molar mass. The value is 0.55. What is the atom economy, which is the mass ratio of product per reactant? That value is 0.55 for reaction 1, indicating 55% of reactant mass is converted to the product. In the same way, we could calculate the raw material cost and fractional atom economy for reaction 2, 3, 4, 5 here. Then you could compare those 5 different reaction pathways in terms of cost and then in terms of fractional atom economy. As a result, R2, R3 and R4 looks attractive from cost and atom economy points of view. Look at that. Those 3 reaction pathways need to have the lower material cost, also higher fractional atom economy. One more consideration is required. Did they have the toxic gases like phosgene? So you could find the carbon monoxide in the reaction 2. As you know, carbon monoxide is very toxic. So R2, the reaction 2, looks less attractive from a safety point of view due to toxic carbon monoxide. So, as of now, we could select R3 and R4 for the preferred reaction pathways. Then let's go to the comparison in terms of the equilibrium constant of activities Ka in the following slide. Then let me think about the chemical equilibrium. Of course, we could use this equation, right? So by calculating the enthalpy term and gives free energy term of reaction from the formation energy, then we could obtain these equations. So let me check it. The first 2 reactions is exothermic. We could recognize it is exothermic because we have the plus sign here. plus means, this is plus, means the delta HR at the standard state is negative signs. Negative enthalpy means the exothermic, right? So it means at higher temperature, the equilibrium constant is going down for the reaction 1 and reaction 2. And reaction 3 and reaction 4 are endothermic. So at higher temperature, we could have very high values of equilibrium constant. That is our expectation. Anyway, let me calculate those equilibrium constant at 100 Celsius degree and at 500 Celsius degree. R1 is great. The phosphogen based chemical reaction is great in terms of equilibrium constant. However, we don't like the toxic reactant involved in the R1. How about R2? Very higher than R1, but at 100 Celsius degree and also at 500 Celsius degree. R3 and R4 too low in terms of chemical equilibrium constant. So R2 is reasonable alternative to the phosphogen based route R1, even if this reaction 2 has the carbon monoxide as the reactant. However, carbon monoxide is better than the phosphogen. Here is the new subchapter about the equilibrium. I'd like to give you very important statement for this chapter. Chemical reaction equilibrium relationships coupled with material balance equations allow us to determine the achievable reactor performance. I'd like to emphasize the end of that statement. To determine the achievable reactor performance, then we'll use the equilibrium condition for the process, or we will assume the equilibrium condition for the final concentration or flow rate. Then find the concentrations at equilibrium for best reactor performances. Use equilibrium constant to calculate the fractional conversion, yield and selectivity at equilibrium. This is for, again, determining the achievable reactor performance at equilibrium condition. Then we can select the appropriate choices of reactor design variables like temperature, pressure, feed ratio, and so on. An example here, reaction at equilibrium. A and B are introduced into the reactor, and then after the reaction we have C and D and E as the products. Of course, we have unreacted A and B here for the exit stream. Here reactants A and B at known flow rates, so two restrictions are given for the input flow rate for each species, and two liquid reactions R1 and R2 of known stoichiometry are given to this reactor. So Xi1 and Xi2 are the unknowns, or the freedoms. Reactor outlet is at chemical equilibrium. It is the most important part of this example. We are assuming that reactor outlet is at chemical equilibrium to find the achievable and best conditions of this process. So we would have two equilibrium constant for 1 and 2, K1 and K2. So let me check the degree of freedom. Freedom, 2 input, 5 output, 2 Xi. So 9 freedoms are there, and restrict 2 flow rates, restrict for A and B, and 2 equilibrium constant for the exit concentration or mole flow rate. Plus we have 5 compounds as the components of material balance equations. Therefore we would have 5 material balance equation. So 9 restrict, then degree of freedom is 0. Then let's solve this problem. Here are the 5 material balance equations. For the reactant, output is equal to input plus generation term. Actually the consumption term. So A and B are consumed in the reactor 1 and reactor 2. The other thing is the product CDE. Output is equal to no input plus generation term inside of the reaction through the reaction 1 and reaction 2. So we have 5 mass or material balance equations, and in this case input variables are already given to you, and stoichiometric coefficient are given to you. Therefore all output variables are as functions of the xi1 and xi2. Okay, and the other thing is the equilibrium constant are given to you. So equilibrium constant is the product of mole fraction of each species with the stoichiometric coefficient. And mole fraction is defined by the molar flow rate in the output stream of species I per total mole flow rate of output stream. And these output variables or total output variables are the function of xi1 and xi2. For example, mole fraction of xb is equal to the summation of all variables here, and each variables is the function of xi1 and xi2. So here is the xi1 and xi2, and the other thing is b out comes from here, mass balance equations or mole balance equation. Then we have the information about the input signal, like input. We know the values already, and stoichiometric coefficients are given to you. So xb is the function of xi1, xi2, or x of species I is the function of xi1 and xi2. Then let me put those xi1 and xi2 functions into k1 and k2 values. Then right now we have 2 equations about the equilibrium constant with 2 unknowns, xi1, xi2. Then you could calculate the achievable and the maximum xi1 and xi2 at the equilibrium conditions. So here is the more detailed example 4.17, reaction at equilibrium. So ammonia process, and Ka is defined as like that because the balanced reaction equation is N2 plus 3H2 is going to ammonia. So this is the nitrogen 2D1 and hydrogen 2D3 with the ammonia 2D2 with 1 over p square, because the summation of stoichiometric coefficient is 2 minus 3 minus 1 is going to minus 2. So the pressure term is going to p to the minus 2. Then Ka was given to you at 25 Celsius degree, like that. And suppose 1000 kilogram more nitrogen per hour and 3000 kilogram more hydrogen per hour for the reactants are fed to a reactor. The reactor operates at 1 atm and 25 Celsius degree, and the gas leaving the reactor is at chemical equilibrium. So it's very important point, chemical equilibrium. So what is the fractional conversion of nitrogen to ammonia? Anyway, at these conditions we could calculate all of the variables. Here is the material balance equation. We have 3 compounds as the components of material balance equations. Then ammonia, nitrogen, hydrogen, and ammonia is the product, so no input plus generation term, and nitrogen and hydrogen are the reactants, so input plus generation term, or input minus consumption term is there. Then we have those equations. It means the output molar flow rate can be described by the extent of reactions like that, and total molar flow out is the summation of those three things. So it is also function of the xi. And then mole fraction of each species is given to you by using this value for each species with the n total in the output stream. So each mole fraction in the vapor phase is the function of xi. Then let's put those things into the equilibrium constant. Put it there, then we have equation. Only one unknowns are there and one equations are there. Therefore, you could calculate the xi, even if it is a little bit complicated. This is the nonlinear equation, so use an equation solving program or a programmable calculator, or using the graphic or trial and error. Then you could calculate the value about the xi. Also, when you get the xi values, you should recognize that the xi value should have the physically meaningful values. For example, xi should not be non-negative. And also, xi cannot be greater than 1000 because the mole fraction is going to the negative value when xi is larger than 1000. So maybe between 0 and 1000. Then anyway, you do obtain a solution like 970 kilogram mole per hour, and all of other variables in the output stream can be calculated by the xi value or the extent of reaction value. Also, fractional conversion is calculated by xi per the nitrogen, the feed stream flow rate, and that was the 1000. So 970 per 1000 is going to 0.97 for the fractional conversion. Let me think about the relationship between the reactor performance and the temperature and pressure. By changing the temperature pressure, then you could control the reactor performance, or vice versa. If you have specified the temperature and pressure, then you could estimate the reactor performance, like conversion selectivity or something like that. Or if you specify the reactor performance at the very first time, then you should find the temperature and pressure for getting that performances. Equilibrium constant is a function of temperature. Then, as you know, the Ka, I mean the equilibrium constant values decreased with increasing temperature for the exothermic reaction, including oxidation, hydrogenation, hydrolysis reactions. Or Ka increases with increasing temperature for the endothermic reactions, including dehydrogenation and dehydration reactions. Or Ka is practically insensitive to temperature for isomerization reactions. Also, the equilibrium constant or the performance of reactors may be influenced by reactor pressure. Equilibrium conversion, I have said, equilibrium conversion can be a function of pressure for a gas phase reaction with a change in the number of moles. If the number of moles decreases as the reaction proceeds, then conversion increases with increasing pressure and vice versa. Okay, so here is the example 4.18, still on the ammonia synthesis. And in this example, we will try to find the temperature and pressure for satisfying a specified the system performances. In the previous example, we observed that the fractional conversion at equilibrium was high at 298 K, I mean 25 Celsius degree, and 1 atm. Unfortunately, the reaction kinetics are extremely slow at this temperature, right? So, you should distinguish between the equilibrium and the kinetics. At a room temperature and 1 atmospheric pressure, the fractional conversion or equilibrium constant is very high for this ammonia synthesis, but it takes a long time to reach the equilibrium. I mean very slow kinetics at this temperature. Equilibrium might not be reached in this lifetime. Ha ha ha. Temperatures of about 350 to 600 Celsius degree are necessary for this reaction to come to equilibrium in a reasonable length of time using modern commercially available catalysts. Your job is to choose an appropriate ammonia synthesis reactor temperature and pressure. Given a target performance specification of 50% single pass conversion, so fractional conversion is 50% for your reactor. 1000 and 3000 kilogram more nitrogen hydrogen per hour are fed to the reactor, so it means the input flow rates are given to you. Assume that the reactor can be designed to achieve equilibrium conversion at the outlet. So we have still the same flow diagram, and balanced equation is here, and let me think about the equilibrium constant as a function of time. So we could use this equation, and the Gibbs free energy of reaction or enthalpy of reaction at the standard state can be calculated from the formation energies in terms of enthalpy and in terms of Gibbs free energy. Those values are given from the appendix B, and also you can find those values in the previous example. So after you have this value, and then finally you have the equilibrium constant as the function of temperature, and this is the exothermic reaction. You can recognize it because delta H is minus sign, so finally this is the plus sign for the coefficient of temperature term. Then from example 4.17, previous example, the mole fractions for the equilibrium constant was described by a function of the extent of reaction, so something like that, right? So we have the equilibrium constant as the function of pressure. So right now we have two equations. One is the function of pressure, the other one is the function of temperature. And let me calculate the extent of J first. Fractional conversion is given to you, and here's the material balance equations. Then from by combining those restricts, then you could calculate the extent of reaction of the ammonia synthesis. Here 500 kilogram mole per hour. Then put this value into here, so K is inversely proportional to the pressure scale with the coefficient at 5.333. So this is the function of the pressure, which is for the equilibrium constant. And the other thing is equilibrium constant as a function of temperature. Then this one, this one is equal to this one. So we could have obtained the relationship between temperature and pressure. For example, at 633K, then you could calculate the Ka value, like Ka is equal to 10 to the minus 6.31 is going to this value, is equal to the function of the pressure. Then finally you can obtain the pressure value like 54 atm. So I means you will obtain the points of temperature and pressure, then plot it here. Then as temperature is going up, the pressure is you should increase. I means again, as temperature is going up, you should increase the pressure to satisfy the fractional conversion at 50%. So right now, from the given specification of the performances, then you have found the temperature and pressure. Here is the final example of chapter 4, which is about the NOx formation. So here we'll try to find the temperature and pressure for a process. A significant contributor to airborne pollution is formation of NOx. Rhymes with LOX, FOX, and SOx, so NOx. Compounds like NO, N2O, and NO2. One of the main sources of NOx is combustion in automobiles, industrial furnaces, and other sources. What is the best way to design burners and internal combustion engines so they don't produce much NOx? To begin to answer this question, we ask, how do chemical equilibrium considerations enter into design of engines and burners? Two reactions of importance are NOx formation and NO2 formation. This NO2 is going from the NO. Again, N plus O2 is going to 2NO, and this 2NO is going to the 2NO2 with additional oxygen. So we have two chemical reaction equations. And both reactions occur in the gas phase and are most important in the hot flame after the fuel has been burned. The equilibrium constant for reaction 1 and reaction 2 are K1 and K2 respectively and depend on temperature as like that. So then we have two questions here. The first question is about plotting the K1 and K2 versus temperature. So the temperature function of K1 and K2 are given to you, and just plot it by using some software or something like that. So this is for the reaction 1, NO formation, and this is the reaction 2 for the NO2 formation from the NO formation. The equilibrium constant of activity increases with temperature for reaction 1, because this would be the endothermic reaction. However, the Ka values would decrease with increasing temperature for reaction 2, because this is about the endothermic reactions. Reaction 2 is much more favored than reaction 1, right? Except at very high temperature. So usually NO2 is dominant rather than NO over the whole temperature range. NO formation is favored only at the high temperature. However, NO2 at low temperature. So at relatively lower temperature, the just from the NO is converted to NO2 immediately. And let's go to the second questions about the equilibrium composition of NO, NO2, and NOx. In this case, we will consider about the NO and NO2. Here is the flow diagrams and the 64, O2, 738, N2, 198, some the other something gases. And then after the flame, then we have the unreacted oxygen and nitrogen with NO and NO2 plus some the other things. And then our assumption is that the compositions of the axis stream is at equilibrium. So Let me try to use the extent of reaction of reaction 1 and reaction 2 to describe the output mole flow rate in the X stream. So input information are given to you for the oxygen and nitrogen, and even inert, then the generation or consumption term is given to you by using the unknown Xi1 and Xi2. So this is the output, and then by using this information you could define the mole fraction of all species in the exit stream by using the Xi1 and Xi2. Then put the mole fraction description to the equilibrium constant term. So K1 is the function of Xi1 and Xi2, and K2 is also function of Xi1 and Xi2. Then at a given temperature, we know the value of K1 and K2 from the temperature function. Then you could solve the problem about the Xi1 and Xi2. After obtaining the values of Xi1 and Xi2, you could calculate the all variables for the X stream of this process. One more things. You should thinking about the physically reasonable constraints about the values of Xi1 and Xi2. For example, Xi1 and Xi2, I mean Xi1 plus Xi2 cannot exceed the value at 64. If this value is larger than 64, the mole fraction is calculated to be the negative value. Well, the other thing is Xi2 should be less than Xi1. Also in the same way for the restriction for the mole fraction. Then, for example, at temperature 15,000 Kelvin, from the temperature function, we could calculate the value for K1 and K2. Very small value, 10 to the minus 5, around there. So, equilibrium constants are very low for both reactions, and then we could easily expect that the extent of reaction will also be very low. Xi1 and also Xi2 would be very small values. So for simplifying these complicated equations, 738 minus Xi1 is going to just 738 because Xi1 value is very small compared with the value of 738. Or this is going to just 64. Very small value for Xi1 and Xi2. Or 1000 minus Xi2 is going to be assumed to be 1000 because Xi2 value is very small when compared with 1000. Then we could simplify those equations with the values of K1 and K2 at temperature equal to 1500 Kelvin. Then we can solve the problem. In this case, Xi1 is equal to 0.34 and Xi2 is the 1.3 by 10 to the minus 3 gram mole per hour. Then by using these values of Xi1 and Xi2, you could calculate the mole fraction of every species in the X stream, including NO and NO2. In this case, the mole fraction of NO is 10 to the minus 4 and NO2 is 10 to the minus 6. And this is the graph for the mole fraction at equilibrium for NO and NO2 over some temperature range like that. So as temperature goes up, mole fraction of NO2 and NOe would increase following the temperature. Then here's the homework. That's it for the chapter about the reactions or reactors.